So did you know that 1 hour of sunlight already provides enough energy to fulfill our entirely global demand of 1 year? If this little globe in the left corner represents our yearly energy use, which amounts to about 16 terawatt years per year, then the other spheres showing the coal, the oil, the gas represent the total reserves that we have of fossil fuels. And this amounts to about 1,300 terawatt years in total. So this means that within the next century, we will run out of these reserves. Additionally, burning of these fuels leads to the emission of CO2, which leads to global warming, so it's absolutely essential that we look for alternative energy sources. If we look at the amount of energy provided by sunlight, we see that this is more than enough to fulfill our entire global demand. So more and more electricity is already based on solar power. In fact, I just read this morning that it is at the moment the cheapest energy source. However, the chemical industry still largely depends on the use of fossil fuels. So how amazing would it be if we could use solar energy not only to generate electricity, but also to make the chemical industry more sustainable?
Yeah, that would be amazing. So why don't we take Mother Nature as an inspiration? A well-known example of a process where light is used as an energy source is in the green leaves of plants and trees. The chlorophyll in these leaves absorbs the sunlight and uses the sunlight to convert CO2 and water into oxygen and hydrocarbons. This is a process known as photosynthesis. And actually, researchers from the University of Cambridge recently succeeded in making an artificial leaf, which you can see on the bottom right. So as chemists, we can take this principle and design materials that can imitate this photosynthesis. If we design semiconductor materials that can absorb visible light, we can produce free electrons. This is what you can see on the top right. We can use these free electrons to do redox reactions. So this way, we might be able to use the energy that is stored in the sunlight to convert CO2 to sustainable fuels, such as methanol, which can then be used in the industry. But light can not only be used to break carbon bonds, but also other types of chemical bonds.
So that means that we may be able to perform any chemical reaction with light. So actually, the corona crisis inspired us to see if we could take these principles to break down virus particles. So as some of you may know, UV light kills virus particles. However, both outdoor and indoor, there's barely any UV light. So what we want to do is to make photocatalytic materials that absorb visible light, use this to generate free electrons, and then use these free electrons to kill viruses. If we look at viruses and bacteria from a chemical point of view, we see that they are all surrounded by a membrane with proteins. And these membrane and proteins are used to enter the host cells. In other words, without these membranes and proteins, they are no longer infectious. These membranes and proteins have a lot of chemical bonds in common. Think about phosphate bonds, sulfur-sulfur bonds, or carbon-carbon bonds. So if we can make materials that use visible light to cut these bonds, we find a general way to inactivate many pathogens. So very recently, we made coatings based on copper oxide iron oxide, and titanium dioxide. And what we found is that these effectively killed coronavirus particles. So this could mean that maybe in the future we can make doorknobs that sanitize themselves.
Yeah, so it would be great to be able to extend this principle and not only break down viruses, but actually maybe anything harmful that can be present in the air. We all know we are all familiar with the smell of a new table or a couch when you place it in your living room. Sometimes the smell can linger for weeks after. And if this symposium were in real life, maybe the meeting rooms wouldn't have smelled as fresh at the end of the day after people have been inside all day. These unpleasant smells can be caused by toxic molecules such as formaldehyde, nonanol, and toluene. These are volatile organic compounds. And not only do these molecules smell bad, they can actually be detrimental to your health and, for example, cause headaches. Now, we want to develop a photocatalytic nanomaterial that can break down these toxic compounds by means of visible light. And this is what you can see in the picture here. On the bottom right, there is a nanomaterial pictured, which consists of a cage-like structure. It's very tiny, called a zeolite. And in the cages, we put very tiny metal oxide nanoparticles, which act as the semiconductors. So these can absorb visible light. And this visible light can be, for example, sunlight, but also light coming here from above or from your office lamp, for example. So it would be great if we could incorporate these kind of materials in a protective layer, such as a coating or a paint. And then we could apply this coating or paint to the walls or to the furniture. And that way you can make air cleaning rooms or furniture.
So that may mean that within a few decades we are able to use the enormous energy provided by sunlight not only to generate electricity, but also to make sustainable fuels out of CO2, or even to make coatings or furniture that clean themselves. The future is bright. Thank you.